Hello everyone, my name is Seyed Mobin Moussavi and I'm a researcher at Völkers at the University of Kassel, and I would like to present the research designed for manufacturing of a digital hollow cross-section beam using interlocking connection. This research has been carried out in collaboration between two departments at University of Kassel, TWE and TFF, as well as Design to Production Office in Stuttgart. The content of this presentation is as follows. I will start with a short introduction. In the contemporary construction, the geometries of the buildings are highly optimized to have a high structural performance. For instance, in the complex Bangkok airport. The manufacturing process of the curved beam supporting a metal-clad seam roof is still a challenging process. One of the most common manufacturing techniques for especially curved parts is 3-roll push bending, which is a kinematic forming process. Bending the standardized profile without a shape deviation to the target geometry is not possible due to the spring back of the material. Another challenge is also final cut, as well as drilling mounting position for connecting elements on the beam after the forming process, which requires scanning tools that makes the process inconsistent and imprecise. Laser cutting technology is typically used for industrial manufacturing applications, and it dominates other metal cutting processes due to its significant benefits in both cost and accuracy. The state-of-the-art projects have shown that methods to rationalize the design of the structural elements, integrating bending active properties of the thin sheet metal and interlocking connection reduces the fabrication and assembly time while increasing the structural performance. Therefore, this research project investigates computational strategy to design and manufacture a curved steel beam using interlocking connections. The computational methodology uses a form-finding approach to integrate the geometric and material characteristics in the deformation process to not only inform the structural performance but also design of connection details. The research follows a twofold methodology of design to fabrication development and physical prototyping. Within the digital development, in the geometric modeling step, the shell model of the beam is generated based on the actual curve and stiffener geometries. In the second step, FEM simulation validates the output geometry through form finding and determines the residual stress and structural performance, such as load-bearing capacity of the beam. This step also includes a generative process which optimizes the design and material parameters. In the last step, digital manufacturing strategies deal with the laser cutting fabrication and plate joining methods. As a first step, a series of physical studies was carried out to determine geometric parameters and relationship between the parts. The system consists of bent slender plates pulled into their target position with inner stiffener plates. Here you can see more models generated based on the same principle with single and double curve configuration. Next, the abstracted construction principles translated into a digital environment. The computational workflow mainly deals with creating developable surfaces based on the actual NURBS curve and the stiffener geometries. The ruled surfaces generated by sweeping the edge of the stiffener plates run through a spring-based relaxation to have a constant zero Gaussian curvatures. The surfaces are then unrolled to the 2D configuration for applying the interlocking connection details as well as engraving manufacturing data. A special focus in the development of the two-dimensional finger joints lies in construction, the structural performance, and assembly details. Parameters such as number and the depth of the finger joints are determined based on the edge length and material thickness respectively. Another crucial parameter of determining the width of the interlocking connection is the correct definition of tolerance in the curved configuration. The simulation step includes assigning the material properties to flat sheet elements and pre-stress value to cables, which is later translated into a connection force acting on the coupling elements between the plates. The output parameters are residual stresses and tension force necessary for assembly. To reduce the self-weight and residual stresses in the beam, an optimization loop was initiated to assess the impact of the geometric parameters on the FEM analysis. This integration allows to set up a generative model in which each set of numeric value gets rated and triggered the next generation. Manufacturing development consists of strategies to assembly process and plate joining. Two strategies have been explored for plate joining. The bolting method allows for orthogonal reversible join between the stiffeners and the bent plates. The second strategy is laser fusion welding, which creates a strong and durable bond through a localized fusion of the two materials. The physical prototype aims to evaluate the accuracy of the resulting geometry as well as structural performance of interlocking connections. The material used for these experiments is 1 mm stainless steel. All of the manufacturing process was carried out at TFF laboratory. A pentagold sample beam then laser cut and assembled using a bolting system. The comparison shows a strong correlation which indicates the simulation model has a high predictive capacity. To determine the load-bearing capacity of the interlocking connections, a simple model was abstracted for the uniaxial test. Different specimens with different placement and amount of weld were fabricated to measure the impact of the welding on the structural performance and stiffness. The structural tests have been carried out in TFF lab. Focusing on the linear elastic error of the test demonstrate although the full edge welding has the highest impact on structural performance, single point welding series already provides double the stiffness compared to no weld connections. As a conclusion, the digital beam promotes the use of laser cutting in the construction industry to create a free-form and highly precise curved beam. This design-to-manufacturing methodology may therefore be recommended as an alternative to conventional complex fabrication processes, which requires less energy consumption and provide higher structural integrity and material utilization. These are our references, and thank you for your attention.